All right. Welcome to the second lecture of online learning operations and electronic markets. So we have kind of a fun plan for the next maybe two or 3 weeks. And let me start by an example of a scientific study that you might encounter in your academic life or non-academic life, depending on which path you're going to take. So here's a scientific study. In economics, there was this notion of correlated equilibrium, which I'm going to talk about today, which is essentially about a game played by the agents, and then there is the coordination device that tells them somehow what to do in a probabilistic fashion. And in econ, this has been kind of a core question for a long time, and many people started studying that, maybe from the classic work of Foster and Bora and Foster, and also the Hart and Mascolell econometrical paper. They're like pretty old papers, but not super old. And then it turns out that there are two connections between something that is more related to online learning, the topic of this course, and correlated equilibrium. So the first connection was about a specific type of learning, which I'm gonna explain today, called no quote-unquote internal regret learning. Last time we talked about no regret learning agents, if you remember, that is essentially no external regret. So there is a more general and more powerful notion called no internal regret. And turns out that if you have learning agents that satisfy this criteria, then the pool of the agents as a whole is going to converge to the correlated. And by the way, I should mention that no external regret is essentially online linear optimization. We are going to talk about the connections further in the course. And somehow there is a bidirectional connection between internal regret and external regret. Like not only this is a stronger notion, actually there is a other way of the reduction as well. So it's going to be a lot of loss in this reduction, but somehow given any algorithm that has external regret, you can also transform into an algorithm that can give you no internal regret, but the rate is going to have a little bit of loss. Then the second object that we will study is something that, again, we are going to talk about in the next lecture, is about a forecaster that is basically trying to predict the state of the world and tells that state of the world to a decision-making agent and tries to have particular criteria in the forecasting called calibration. I'm not going to go through the detail, but then it turns out that calibration, and if you can design a forecaster that has the calibration, will result in correlated equilibrium. So somehow by combination, so somehow agents in a game that they listen to a calibrated forecaster are going to eventually converge to correlated. We are going to learn all of this. And everything here is probably like from 1995 all the way to 2007. And there are a lot of follow-up work to that. Later, people realized that there was this very smart guy, David Blackwell, that had a seminal work, David Blackwell, that goes all the way to 1956, that basically thinks about something similar to a zero-sum game, but when you have vector value pairs. And I'm going to explain that in the class. This is kind of like a very abstract game, and he solved that abstract game. How agents not only can play the one-shot version of that game, but also how they can play the sequential version of that game. And then it turns out that, amazing, this is actually more general than all of this. If you can solve this problem, you can find no internal regret learning algorithm. You can find no external regret learning algorithm. You can also directly find the calibration in forecast. And therefore, this is kind of like the stronger problem among all of them. But that's not the end of the story. Now that we know a lot about first-order methods and kind of optimization algorithm, optimization theory, we know that this guy is actually not but online convex optimization in disguise, and somehow there is a bidirectional reduction between Blackwell approachability without any loss to online convex optimization vectors. And this is a modern treatment. Somehow this connection was discovered, I think, in 2012, if I'm not mistaken. And this is now the picture that we are trying to study in the next 2-3 lectures. Like this connection between correlated equilibrium, different variants of no regrets learning, calibrating forecast, and Blackwell approachability. Right? Yes.
A quick question. So when you talk about agents, these are like they are not linked together.
So they're playing a game, but they lead them to some sort of correlation. I'm gonna explain. So let me try to set up my lecture by basically first talking about what I call correlated equilibrium. Correlated equilibrium in normal point games. Okay, so let me do the basic setup. Imagine you have n players. Each player has an action set or action space. For the sake of simplicity, I'm going to assume that these action spaces are finite. So action space AI. And then the player also has a utility function UI, which essentially maps a profile of actions similar to the last lecture, A1, blah, 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 A, and to some, let's say, non-negative number. Right? So we talked about these agents playing the game and trying to maximize utility. We talked about snatch equilibrium, so on. Now, here's kind of like the picture I want you to have. Imagine I have these guys. These are my N agents. Sometimes they call them players, sometimes agents. And then we have a game that they're planning to play. And then you can try to analyze this game at a stable state, aka an equilibrium, so on and so forth. That's not what I'm planning to do. Instead, I'm planning to attempt the following. So imagine there's what I call a coordination device. So this coordination device going to have a conversation with my agents, some sort of conversation, and try to convince them to play a profile of the strategies that makes sense. Okay. Now, with this abstract notion, let me define two solution concepts. Definition one, coarse correlated equilibrium, abbreviated as CCE, coarse correlated equilibrium. And then another more general solution concept, just a correlated equilibrium, abbreviated as CE, correlated. So what is coarse correlated equilibrium? So it is, let's say, joint probability distribution pi over the space A1 blah, 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 to AN, basically joint distribution over actions, such that the following is true. For every agent I, and any deviating strategy A prime in the action space of A, I know that the expectation of UI A is greater or equal to the expectation of UI A prime and A minus I. When A here is drawn from P, and here is the same. So A is drawn from P, or equivalently A minus I is drawn from the marginals for all coordinates. Okay. So the joint distribution over actions that players say, all right, so the coordination device says that, hey, everyone, I tell you this distribution. You should commit that you play with this distribution, meaning that you're gonna realize your actions jointly from this distribution, And then this distribution is chosen in a way that no one at the ex ante stage, before realizing the realized suggested action by the coordination device, would better off by deviating to a different strategy. So your expected utility, if you follow this joint strategy at the ex ante stage when you haven't yet seen the realization of the action from the distribution, is always larger if you follow the distribution versus any deviation strategy, assuming the others are following the distribution. Right? There's some sort of like commitment of the agents to a distribution at ex ante stage of the game. Ex ante basically means time 0 before anything happens. Now, this is not exactly what really makes sense when you think about the coordination device. Let's go with the other notion. So again, a joint distribution P over A1 to AN is a correlated equilibrium if for every agent I and for every action A that is potentially played by this player because it was suggested by the coordination device, and also any other action A prime that is potentially a deviation of strategy, you have the following. So here is the way I would like you to think about it. Suppose I'm the coordination device. I actually suggest you a profile of actions, A1 to AN. So each player only sees the corresponding suggestion for that player, not the other suggestions. Now, the question is, now that I give you this suggestion, would you be better off deviating to another strategy, knowing how this suggested is generated, assuming that the other players are also following the suggestion? So from perspective of player R, am I doing the right thing if I follow the suggestion, assuming that the others are following the suggestion? The difference is that now we are at the exposed stage. Basically, you have seen the realization of the suggestion from the coordination device distribution. Pretty much the same, but the only difference is that now you have to update your belief based on the realized action that you have seen. So therefore, but you want to guarantee the following. So expectation of, let's say, UI of A and A minus I, condition on AI to be equal to A, when A, well, so yes, let me call this, yeah, so it's a little bit of bad notation. Let me call them A prime and A double prime. So UI of A prime, A minus I, condition on AI equal to A prime, when the entire A is drawn from P, should be greater or equal than expectation of UI, A double prime, A minus I, condition on AI is equal to A prime, when A is drawn from P. So I'm looking at the pair of actions, A prime and A double prime, then condition on the event that the coordination device is actually suggesting A prime to player I, then once the player I is updating her brief, assuming that the others are also following the correct conditional distribution, is going to be better off by following what has been suggested. So there is a mathematical analogous of this condition. Let me actually write it here because I'm going to actually use this, which is multiplying both hand sides by the probability that A is equal to A prime. So I can say the expectation of UI, let's say, A prime and A minus I, indicator that AI is equal to A prime when A is drawn from P is greater or equal than expectation of UI, A double prime, and A minus I, indicator that AI is equal to A prime. Somehow this other definition is saying that, hey, I'm just gonna look at the sample paths of this stochastic process. This is a stochastic system where the suggested actions are equal to A prime. And only if that's the case, I want the agent to be better off playing A prime over any other strategy. Right. So let me make this a little bit more clear through an example. This is kind of like the example that people typically use when they want to explain the concept of correlated equilibrium. It's called traffic lights. Traffic lights. It's a two-player game between two cars that they arrive at the same intersection. You have, let's say, driver number one, driver number two. Each of them has a strategy, which is going or stopping. The go or stop. Let's say they are maximizing utility. If both of them they go, then they collide. So that gives the utility 0 and 0 to both agents. Let's say if they both stop, it's going to give them some other utility, 4 and 4. Now, if driver one goes and the other driver stops, then driver one is going to get a utility of 5, but the other one is going to get a utility of 1, and vice versa if the other direction. So now, if you think about this game, it has multiple mixed Nash equilibria. So one is the pure strategy 5-1. The other one is the pure strategy 1-5. Why? Because if I'm at 5-1, no one actually has any incentive to deviate. So if I'm driver one, I'm getting 5. If the other one is playing stop, then if I switch to stop, 5 reduces to 4. So this is not a deviating strategy. And same as for the other player, so if I'm stop, if I go to go while the other player is going, then 1 reduces to 0. So therefore, this is not a deviating strategy. There is also a mixed Nash equilibrium, which is, I believe, half-half. Yeah. So imagine B1 is going with the half-half, and B2 is going with the half-half strategy between F and G. But this is also going to be a mixed Nash. Not hard to check that. But really, what you want at an intersection is that, let's say half of the time one goes, the other one stops. And then the other half of the time, the reverse happens. That's exactly what the traffic light does. And now, suppose I'm the coordination device, and I commit to the following joint strategy. So my joint strategy is going to be the following. So I'm going to suggest this with probability half, and I'm going to suggest this with probability half. So this is going to be P. And this turns out to be actually correlated. Not hard to show that it's correlated. And I should say any mixed Nash equilibrium, of course, is a correlated equilibrium. It's just a correlated equilibrium that has a product form. Any correlated equilibrium also is a coarse correlated equilibrium, because if you have a correlated equilibrium, any correlated equilibrium, if you take another expectation, of course, you get this other constraint. So exposed condition is always stronger than the example condition. Therefore, we have this, let's say, corollary. The space of all the mixed, the space of all the pure Nash equilibrium, P and E's, is a subset of mixed Nash equilibrium. And this is a subset of correlated equilibrium, and this is a subset of coarse correlated. This is kind of like the game theory picture right here. Now, here's the goal. Can we get rid of the traffic lights? can we somehow replace this coordination device, which turns out to be helpful, right? So when you think about this game, the traffic light was really helpful because none of these mixed match equilibrium really makes sense. This one is chaos, and this is just asymmetric bad equilibrium for one player. So none of them is really good, but this one is actually pretty good. So can we actually somehow get rid of the traffic lights? And what we are going to do is replacing coordination device with online learning, because this is the course in online learning. So we're trying to do that. Step one, we're going to consider hedge algorithm, basically full information online learning algorithm for the finite expert problem as before. And we assume that all of the agents in the game are trained already. So let me write it down formally. Assume all agents run as no, I'm going to use the word external for a reason that will be clear. So no external regret learning algorithms. So what does that mean? Formally, if let's say A1 all the way to A capital T in T rounds of play is the sequence of action profiles played by all the agents together. The sequence of action profiles played. Then we have the following guarantee. From the perspective of every single agent, or every agent I, somehow the agent is better off playing what he is playing using the online learning algorithm versus any fixed strategy, or versus any fixed. So what does that mean? That means that let's say summation T from 1 to capital T, UI, the utility of agent I, when he's playing strategy AI at time T, which is the strategy that the agent is using. But this notation is for vector. So it is a vector. I'm going to use this a lot later. So summation T from 1 to capital T, UI AIT, A minus IT, think of it as a matrix, which is or vector, which is strategy of all other players except for I at time T. So this should be greater or equal than summation T from 1 to capital T, UI of, let's say, strategy A prime, A minus IT, minus what I call the regret external at time T. And this should be true for every action A prime in the strategy that is defined. Suppose this is true. Now here is first theorem. If all agents are doing step 1, then they converge to, well, maybe more formal. Then the following strategy, let's say uniform distribution over A1, like A1, all the way to A capital T. And looking at the capital T vectors, we can uniform distribution over those. Basically, empirical distribution of how many times the action is played by each distribution, by each player. Then this is defining now a joint distribution over actions of all the players. And this is going to converge in some particular sense, which I'm gonna write down, to a coarse correlated equilibrium, not equilibrium. Proof is literally not even a proof, it is almost a definition. Well, I know this is true. For every agent I. Yes, one.
I have a question. So A prime is a strategy, right? So A is a set of all strategies.
Right.
Isn't it?
You mean curly AI?
Clearly, yes.
It's just a member of. So from a step one, I don't know how to say it, just divide both by capital T. And then what is going to be the left hand side is essentially the expectation. Let me call this like T. This is the expectation of, let's say, UI when A is drawn from P, basically equal to 1 over T, summation T from 1 to capital T, expectation of UI A minus IT, right? By definition of the uniform distribution. So for each of them, you get a utility and then you take that. I'm not using any fact about linearity of utility or anything, like linearity of expectations. And now, because of the step one, this is going to be greater or equal than 1 over T, summation T1 T, U are mediated by J prime, while the other are playing the same thing, minus my average regret. Oh, I should have said one thing that when I say step one, I implicitly know that this is sublinear, so no regret. And no regret is the following, so no regret means that limit of our external T divided by T as T goes to infinity is essentially equal to 0. So the average regret goes to 0, or basically the accumulated regret is sublinear. Right? And now this is basically the expectation of utility of I when deviating to A prime and others are going with the marginal distribution E minus I minus the error term. And now when T goes to infinity, this converges to 0. So this goes to 0 as T goes to infinity, and hence what we want to show. Almost at the level of the definition. Yes, Pasha.
I have basic questions. So the games that you're describing here are sort of one shot, right? You want to play it once, right?
Correct.
And
But
then-
but instead of playing it once, I'm gonna play it capital T number of rounds, similar to last time. Do you remember like the two players playing zero sum game? And then I'm looking at the average play, and somehow saying this average play converges to that.
So in other words,
Yeah.
computing this CCE or C or all of those are complicated, and online learning is sort of an algorithm to.
Good. In fact, this is the proof that computing this is easy.
Yeah, so you can use.
Right, so you can run online learning algorithm as long as you can run the online learning algorithm for a long time, which I haven't told you that much about it. So page algorithm, as long as we have polynomially many actions, we can run it in polynomial time. So therefore, as long as you have polynomially many actions, you don't have a lot of actions, then you can run the online learning, therefore you can compute this. I'm going to show it next that this also is computable. And the funny part is that not only they can be computed using online learning, we can actually show that the set of correlated equilibrium in particular is a polytope. If you want to even characterize a polytope, all you want to show the existence or find any correlated equilibrium, all you need to do is to be able to solve a linear program with polynomial size. So the complexity of computing C and CC at the level of complexity of solving a linear program of a small size. But then, when we come to these two guys, pure Nash equilibrium not always exists, even in finite game. Mixed Nash equilibrium always exists in the finite game. That's Nash Nobel Prize winning work. But finding a mixed Nash equilibrium is computation hard. There is this class of computation in hard problems called PPAD, PPAD. And this is actually, we conjecture this is harder than NP hard. So somehow finding a mixed Nash, even though it exists, is computation difficult. And that's kind of like, as you make the set larger, it is going to be easier to find the correlated equilibrium, but you might be very well in a situation that the correlated equilibrium that you find is not actually mixed, it's not a product distribution.
So, in other words, the CCE, the algorithm you suggested here, it has this online nature. It can solve like a one-shot, like linear program to get it.
Yeah, so in fact, you can solve linear programs using online learning. We already saw an example of that, of a zero-sum game. But that result generalizes all the way to packing LPs and even non-packing LP. Check the paper Platin, Chamois, Tarbush. That's the first paper that shows how can you use multiplicative weight update to solve packing LPs. And now we already know from optimization theory that we can even be done faster. You can do optimistic gradient descent and get the faster conversions to traditional theory. But anyways, that's the story for another lecture. But now let me show you how you can get convergence to correlated fields. And that brings me to this kind of deep notion of regret. Because usually when you think about regret, you're comparing the algorithm to the benchmark. Now I'm going to compare the algorithm with itself. Sounds a little bit here. Let's formalize that. So definition. Internal regret. So how many of you are familiar with internal regret? Raise your hand if you have seen this or a version of that somewhere else. All right, cool. For people who are doing reinforcement learning, it's a little bit similar to policy regret. Not exactly that, but has the same nature. So what is it? So imagine the following. So a sequence of actions. Now I'm looking at the online learning problem. Remember, in the online learning, we had, let's say, n number of arms that you were pulling. Each time the player is actually picking a distribution over arms, drawing something from that distribution, or let's say one of the actions. And the other player adversary is assigning a reward to each arm. The adversary in principle could be adaptive or oblivious, as we discussed last time. So for now, let's say it is adaptive. The sequence of arm pulls, let's call them, or maybe actions. A1 to a capital T, and a sequence of rewards, or sequence of reward functions, say. R1 to RT, where you should think of each of these RIs as a function that maps the action space. Let's say they all belong to the action space, which is numbers 1 to n. So it maps the action space to, say, some non-negative number. The sequence of arms and a sequence of reward functions are given. So consider what I call an advisory function. So what is this advisory functions? Think of it as a function f that maps numbers 1 to n to numbers 1 to n. It suggests an alternative action. So suppose you're investing, so there are different stocks that you are buying every time. There are n of them. At each time we decide to buy maybe 1 or 2 or 3. But then there is this advisory function coming saying that, hey, every time that you bought Microsoft, maybe you were better off buying IBM. Every time that you bought 2, you were better off buying 4. So it tells you kind of a mapping. It doesn't need to be a permutation. It's just a mapping from 1 to n to 1 to n that says every time that you picked I, you were better off picking f of. So this is what the advisor is saying. And now you want to do online learning the way that you prove the advisor wrong. So what does that mean? So we say we have, in this setup, we have let's say no internal regrets. If the following false. So what I expect is the following. So what I'm looking at the summation T from 1 to capital T. And then I'm looking at R, T was better. So RT of f of I minus RT of I minus f of j of okay, so RT of f of AT, that's the action I'm picking, minus RT of AT. Indicator that at time t, oh, that's it actually. Yeah. I want this to be less than or equal. Let's see if I'm using the same notation as my notes. So I'm going to copy the different notation again. So this is going to be at most R of t. And the limit of R of t divided by t as t goes to infinity converges. The internal regret is the following object. So let me now define internal regret. Let me pick a name for this guy. Let's call that R of sequence A, T, sequence RT, and maybe T. So for a given sequence of actions, I'm going to or for an online algorithm, I define the internal regret. R of int as a function of t, to be basically the max of R AT, RT, and T over all selector function or advisory functions. Is it clear? So we have, let's say, an online algorithm is drawing these actions, A1 to capital T. There is a second player adversary is assigning rewards to the different actions. Now, for that sequence of actions and rewards, I can look at this notion, which is basically the following. So every time T, I'm going to look at the reward I would have get if I had played f of 18 instead of AT. And I look at the difference between the reward I'm currently getting, and I'm accumulating all of these pairwise regrets. Let's call that, maybe I can going to call this R of AT, RT, and T. For RF, maybe this is a better notation, because the F appears somehow. Not increases. Let's call that RF. Which is basically the regret that the online algorithm gets is the advisory function f that maps action 1 to n, 1 to n. Now, the internal regret is defined to be the worst case of such regret when you are looking at all possible advisory functions. Right? is trivial. R of internal T is always greater or equal than R of external T. Why? Because one choice of arbitrary function proof f constant. The one choice of arbitrary function is as long as f is always picking the fixed action. So if at every time t I'm picking a fixed action, then this is the external notion of regret that we had at fixed. At every time t, I'm just going to go with action A. All right. So now let me go with another definition which turns out to be helpful. That's what they call swap regrets. Let's say I'm focusing on two particular actions, fix maybe actions A and B. And now I'm gonna look at all the rounds that the algorithm played B, if any. And then I say how much extra benefit I would have received if I had played A instead of B. It's a slightly different notion. So again, I'm fixing two actions this time. So previously I was just fixing a selector function. Now I'm fixing two actions A and B. And then I'm saying, look at all the rounds in which my online learning algorithm played B. And imagine in all of those rounds I had played A. How much extra benefit I would have received by this deviation in only those rounds. So therefore I'm going to define this notion. Let's say R hat of, again, the sequence AT, the sequence RT and T, which is equal to the following. So summation T from 1 to capital T. So I'm going to look at RT of, let me go with R hat of A and B. RT of, this is the deviating action. This is the other action. But I'm only going to look at the rounds in which AT is equal to B. And I didn't write it down, but you can also think of the expectation of this quantity. So like expectation of R hat A and B, if you have a randomized algorithm, for example, is going to be equal to the summation T from 1 to T, essentially RT A minus RT B times the probability that the algorithm is playing B. And now I'm waving my hands a little bit. If you have an adaptive adversary, then you need to think of the correct filtration, etc. With those notations, I would have messed up the entire whiteboard. So I'm not going to do that. In your head, assume that you have an oblivious adversary that commits to a deterministic sequence of rewards. I'm not going to answer any questions about what would happen if you have an adaptive adversary. Come to me after the class. That's the question.
No, it's another.
All right, go.
It's not that board. Is this in the proof? The second one shouldn't have expectations, right?
What do you It might be a random sequence of action.
No, AI is a strat.
It might be a random sequence of action. But think of it as a random sequence of actions, then I need the expectation. If it's not a random sequence of actions, then I agree with you. Let's go with deterministic, then I don't need this. You're right. So if I had expectation, I
That's where I should also have.
But this whole thing works if, for example, this was a random algorithm.
Then your constraint in the previous one also had expectation, yeah, for each
Yes.
one.
I assume that everyone in this class is mathematically mature enough that you can assume in your head if you have randomized strategies, you are going to take expectation from it. I'm just, because there are a lot that I have to cover, so I'm going to go with the simplest version. Right. Now let's see what is the difference. Okay, so does anyone know how internal swap figures are connected? Do you have any ideas? So I claim that swap regret is like a special piece of internal regrets. Write down a lemma. So lemma. Let me first define the swap regret definition. Similar to above, swap regret. Let's call this parallel regret. Because here I'm fixing to action. Swap regret is basically the maximum over all the pairs of action A and B of R hat AB of sequence RT, sequence AT, sequence RT, and T. So this thing I'm going to call it R of swap. Okay. So now I'm looking at the worst case pairs of action that gives me the maximum pairwise regress defined as before. Sometimes we can call this swap regress, sometimes called the worst case swap regress. So think of it as two actions, and all I care about is looking at all around and playing one. And look at the deviation in utility I get if I deviate to another action. So now lemma R of swap is actually smaller than R of internal T. And this is at most n times, n is the number of actions, R of swap. A and this B. So A is trivial. Why? So as I said, I claim swap regret is a special case of internal regret. Consider the following advisor functions. I'm going to call it f of a b of x. So this is going to be equal to the following. So I have an advisor that every time that action B is played is going to suggest A, and every time that any other action is played is going to suggest the same action. So f a b of x is going to be equal to A every time that x is equal to B. And if any other action is played, it's going to go with exactly x. So therefore, in rounds that the algorithm haven't played B, there is no real deviation. So they're just in the same action. And in other rounds, there's a deviation to B. So the internal regret is the worst case among all the advisories. So if you restrict yourself to these advisories, it's just going to make the regret smaller. Therefore, A. Now for B, that's kind of a simple proof as well. Let's write down so let's write down internal regret is going to be summation T from 1 to capital T, R of f of AT minus R of AT, right? Now I'm going to divide my rounds into rounds in which a specific action is played. So I'm going to write it down as summation over I from 1 to n. These are my actions. And now at every round T from 1 to T, I'm only looking at that round if that action is played, if AT is equal to I. And then I look at, again, the R of A T minus R of AT, R of F of AT minus R of AT. But you know, in that round, A is equal to I, so you can just replace this with I and replace this with some F of I, which is for I is just another action, whatever it is. Now, this has the form of swap recurrence. For a particular pairs of a strategy, fixing I, so you're looking at I and F of. Therefore, this is going to be as follows: summation I from 1 to n. Oh, so this is R hat of action F of I and I, then T, and this is at most n times R of swap. Basically, all I did is divided time into different epochs where in each, not an epoch, a different round, different buckets of rounds where in each bucket I have played the same action. And I looked at the regret I would have received on their advisory function F in those rounds, and then I summed up for all actions. Nothing really comes. All right, so why did I talk about internal regret? It turned out that we can get rid of the traffic lights as long as the agents are running online learning, rather than obtaining a low external regret, they actually obtain no internal regret. So now I'm gonna do the following. So step 2, assume all agents run a no internal regret learning algorithm. Formally, if the sequence A1 to AT is the sequence of action profiles played, and here let me also assume that maybe they have swap regret in the swap. So okay, if the sequence action profile played, then we have the following. All right, let me rewrite this part. Make it clear. Which I don't have to. Here, I'm going to assume that basically for every action, so I assume that my agents are actually using no swap learning. Therefore, for every action, for every player I, for every action A prime and A double prime, see now it becomes kind of similar to the definition of the correlated. For every action A prime, which is the one that is going to be suggested by the correlation device, and A double prime, which is the possible deviation, I have the following. It's a summation T from 1 to capital T, UI, of. If I play A double prime, and the other players are playing A minus 1T, minus my utility, if I had played A prime, if others are playing A minus IT, in all the rounds in which A IT was equal to A prime, this is no more than or swapped. And now the no regret learning will be the limit of R swap T divided by T as T goes to infinity equal to. Let's see if this is easy to digest. All right, so I'm running online learning. All of the agents are running online learning. I'm looking at the board from the perspective of I. So the others are playing this strategy A minus IT, A minus I. So you should think of this as the reward of agents I when he's playing A double prime. And this is basically the reward of agent I when he's playing A prime. I'm assuming the other players are playing a certain profile of action at every single round, defined by A minus IT. And now, from my perspective, if I look at all the rounds in which I'm playing A prime, and I accumulate the deviation in utility I would have get by deviating to A double prime, then the summation should be no more than the R sum. If I'm running a no swap learning regret out. Is it clear? Now, so if all agents are doing step 2, then uniform distribution over A1 to AT converges to a correlated. Right now, I want to actually just delete this. Proof. By step number 2, again, this is almost the same thing, right? If I divide this by capital T, then essentially I have, write it down. Then I have expectation of, let's say, utility of I. Oh, by the way, so I'm using the second definition of correlated equilibrium, right? So I had this analog mathematical definition. The one was using conditioning, the other one was using indicator function, using the indicator. The expectation of UI, A double prime A minus I minus, okay, so when indicator that AI is equal to my action A prime, when this entire profile A is drawn from P, and this is P now. All right. So this will be equal to nothing but just 1 over T summation T from 1 to T. I know it's boring, but let me actually write it down anyway. So UI A double prime A minus I T. Indicator that AI T is equal to A prime. And if it was a randomizer strategy in your head, just replace it with the probability that you play. So there's really no difference. But this is now because of step 2 is going to be greater or equal than this guy minus the regret, which is 1 over T, summation T from 1 to capital T, UI of deviating to A double prime, when others are saying A minus I, and I am playing A still A prime, so minus the R swap of T divided by T, and then this guy is nothing but just the expectation of UI, A double prime, A minus I, indicator that AI is equal to A prime when A is drawn. So this is greater or equal than that minus something that converges to 0 at this go to infinity. Therefore, this is converging to a correlated. Kind of cool, right? All right. So I can get rid of the traffic light as long as I can have agents that they have a small internal regret. Now the question is, can we get a small internal regret? Because we already showed how we can get a small external regret. It turns out, okay, so what was the smallest external regret we could get for the best expert problem? If you have n arms, I think I showed you, or maybe I mentioned that basically by using a anti-concentration log deviation bound, we can show you cannot do better than a square root of T log n. That's the best bound we can get in full informational dynamic. It turns out that for, say, swap regret, there is less we can do. So here, which I'm not going to show from Long and Mansour in 2007, right? Is that 2000? Do you remember?
I think so.
2007. They basically show that swap regret is at least a square root of T times n. So there is a force dependency on n. And if it is not clear, so because of this lemma, somehow in your head, you should assume that as long as you have vanishing in time average swap regrets, you get vanishing in time average internal regrets, there will be a loss of factor n, which we are going to get rid of. But if we put that aside, so essentially vanishing swap and internal are equivalent up to terms that depend on it. Now, swap and external, we kind of want to show some sort of equivalence, but we should also consider the following, that the information theory lower bound for swap regrets is a square root of Tn, which is already different from the information theory lower bound that we have for external regrets, which is the square root of T log n. So let's recall our external regret of T should be at least the square root of, or is equal to, we know that achievability, theta of a square root T log. Right? Now, here is theorem number 1. There exists an easy algorithm that obtains swap regrets of at most square root T n log n. So if you have been to Abrams class, I assume this is what we probably covered, because this is his result. So this is, oh, this law is Abrams law at TTAC. I should mention that. And this is also from Blom and Mansour, 2007. And theorem number 2, sorry. This is a reduction. Not really a general algorithm. It's not a specific algorithm. It's a reduction. It's a reduction from internal regrets or swap regrets to external regrets. Basically, as long as you give me an algorithm, a square root T log n algorithm for external regrets, I'm going to give you an algorithm which is the square root Tn log n. Okay, so that's a reduction. Theorem number 2. There exists a more complicated algorithm that obtains R of swap T is no more than a square root Tn. T log n. And that's the funny part. This is Blackwell 9056. So you should expect that the better result appears after. I don't think when Avrim and Ishai wrote this paper, they didn't know this connection. This connection was discovered later. That basically by cleverly using Blackwell approachability, you can actually get the right square root and math. I'm going to show both of these results in this lecture. All right. I'm going to show the reduction, then maybe we can have a break after, and then we're going to be back and talk about Blackwell approachability and how to get the parts out. What I'm going to show you is actually genius, though, I should say. Even though it doesn't give you the optimal regret bound in some sense. I think it's much less mechanical than using Blackwell approachability, which I will do next. And somehow it is really smart. And if you haven't seen this before, maybe this can be the takeaway message of this lecture. I'm not sure exactly how they come up with this, but expose it is quite easy. Expand it, if not, so I just call it genius. And I should say the complicated part of Blauman maps in terms of technologies and techniques that they develop is actually the lower round. The upper bound, which is what I'm going to show, it's just smart, but proving it is quite easy. So let me describe what I call the reduction here pictorially, and then I'm going to show you why it works on that. So this is the picture I would like you to have in mind. So the main idea is that, hey, I have n actions. Now I'm going to run n parallel algorithms, one corresponding to each action. And then these parallel algorithms together, they're going to decide on what distribution of actions I'm going to play at the end. So they're going to talk to each other in kind of like a smart way, and then they come up with the right distribution from which you have to draw the final action. And because each of them is a full information external linear learning algorithm, so you need to design essentially what feedback you give to them, what's the reward that they receive in every round. And the reduction is basically about two parts: how to design the rewards, the feedback for each of these algorithms, and second, how they communicate to come up with a distribution or actions in every single. So this is how it works. And if you ask me, do you have any intuition? I have some, but I don't think by majority this is considered intuition, so I'm not going to tell you what that is. If you want to know more, come to me after the class. I can tell you what is kind of like my high-level intuition about this whole structure. All right, so I'm going to have these guys. Let's call them and one, and two, n. At every round t, at round t, what's happening with each of them is spitting out a distribution. And by distribution, I mean a distribution over n actions. So this guy is going to give me maybe q1t, which is a vector. So it's going to give me q2t, which is again a vector. And then this guy is spitting out qnt, which is a vector. Now they're going to talk. I'm going to tell you how they are going to talk. After they reach the conclusion, we are going to output the distribution. Let's call it P of t. And now this is online learning, right? So you're going to receive the feedback, let's say a vector RT at before. Okay. So now I need to tell you how they communicate and what is the feedback that you guys receive, because after that you're going to receive a feedback that means there's a different color. Feedback. So as for the feedback, here's what I'm going to do. So I'm going to say, well, somehow this is the probability over actions. I'm going to divide proportion to those probabilities, the reward I receive between these guys. So I'm going to give a vector. Again, it's not just one number, right? So each algorithm is an algorithm for n action on a learning. So you would give an entire vector as feedback. So I'm going to compute pt at coordinate 1, which is a scalar, and I multiply that by RT. So that's going to be the feedback that this guy is. And then this guy's pt2 times RT. And this is the feedback. So I was scaling down the feedback based on their contribution to the final action. And this guy is going to receive Pn of, maybe it's just a bad notation, so it's, let me do the fun. So this is P1, this is P2, so these are the scalars, right? Now then, Pn, and then RT there. Now, this is the genius part. They're going to come up with an aggregator in the following way. So imagine that we define this matrix Qt, which has Q1, Q2 to Qn on its rows. So I'm going to have Q1, think of them as row vectors now. Q1t, Q2t, all the way to Qnt.
Are these actions?
You mean these guys?
Each queue.
Think of them as a mixed action, basically distribution action. So yeah, so you're right. So this is that is a transition kernel. They sum up to 1 in every row. Yeah. And now kind of maybe you're on the right track. Thinking of it as a transition kernel, I'm going to find the stationary distribution corresponding to the transition kernel. So PT is such that right, think of this as a row matrix, row vector. It's basically P times Q. So what does the algorithm do? At every time T, you first ask it's going to give you a distribution. You form this matrix Q. It's going to be a transition kernel of a finite state Markov chain. And it always has a stationary distribution. Maybe it's not unique because the chain is not reducible. But regardless, it always exists. Now find the stationary distribution, play an action from the stationary distribution. Then you receive a feedback, full information feedback. Doesn't have to do anything with what you draw. It's a full information, you get to see entire vector. Now divide it based on P, give to the algorithms, update their next action, and continue. That's Glom and Mansour's algorithm. All right. Now let's see how it works. Right. So the first thing that you're going to write is basically, hey, each of these algorithms is running with no external regress learning. So let's think about their corresponding online learning problem. For, let's say, algorithm I, right? Here is the guarantee I'm going to get. So I'm going to have the following information T from 1 to capital T. Down. Right, so Q P of I T times R T as a vector dot product with Q I T. Sorry, it's really a bad notation, so bear with me a little bit. So let me tell you what this thing is. So PIT times RT is the reward vector of online learning algorithm for online learning problem for algorithm I. And this is the distribution actions generated by that algorithm. So this is going to be the perceived expected reward of that algorithm. Right? So now you know this is greater or equal than any other fixed strategy because there's no external regret, maximum Q in delta N, summation T from 1 to T, PIT times RT dot product Q minus, all right, so let me be a little bit careful here. I'm going to call this Ri, and for a second you will see why I'm actually using Ri. So it's going to be a function of somehow T, but let's call that Ri for now, just a quantity. Is this clear? Now, the next step, I'm just gonna add up these guys, I from 1 to n. So therefore, by adding up, summation I from 1 to n, summation t from 1 to t, e I t r t dot q I t is greater or equal than summation I from 1 to n. And then, so here I'm maximizing, basically finding the best fixed action given the reward structure. But the best fixed action is not a mixed strategy, it's always a pure strategy. So I could alternatively, rather than optimizing over the n-dimensional simplex, I could just pick one action, right? So summation I from 1 to n, t from max over all actions, alternative actions, j in m. And then I have summation t from 1 to t, p I t. If I pick action j, this is just going to give me RTJ. Right? So if I pick action j everywhere, then at every time I'm just going to get the j's reward. And then this whole thing minus r, which is my real. So this is real. Okay. All right. So here's the funny part. So if I swap the order of the summations here, then this term is going to be equal to the summation t from 1 to capital T, summation I from 1 to n. So I'm going one path over all the rows of Q with probability P I T. Q I T. This is the row matrix, let's say, and this is the scalar. And then the whole thing is going to be dot producted with RT. Again, algebra, but you can swap the order of the summation, then RT comes first. So you have the summation over everything that has I first, and then you're basically adding up these rows with weights that are equal to PI. And remember, P was the stationary distribution of the transition kernel. Therefore, this quantity is nothing but just P itself. So this is going to be basically the vector P here. So we're almost there. I'm here the summation over I. So we're almost there. Now let's think about this. Here, left-hand side is the reward that you basically get. What's on the right-hand side is the reward that you get. So, okay, so let's pick an advisory function. Maybe that's the best way of thinking of it. Let's pick an advisory function. Let's say I'm picking f, which is an advisory function. Then I can say this is greater or equal than if for every I, rather than picking the board action, I would have played the action suggested by the advisor. The summation I from 1 to n. So now I'm going to pick f of I rather than j. So then I would have received the following. So summation t from 1 to capital T, p t I, the probability that algorithm plays action I, multiplied by RT if you had played action suggested by advisor, which is FJ. Right? And then you have the minus of RI. So let me rearrange the terms so that you see this is actually internal regret. So this is all this is saying is the following. The summation T from 1 to capital T, summation I from 1 to n, right? PTI times RT RTI minus PTI times RTJ is at most, sorry, but this is RT of Fi, and this is RT of I. So I'm moving this to the right hand side, moving this to the left hand side. Then summation of PTI RTFI minus PTI RTI is at most summation of RI. And this is the expected internal regret when you are looking at the advisory function F. Because think of this P as, so you can break it out. You can write this down as the expectation of essentially indicator that your action at time t is equal to I times RT of Fi minus RT of I. So this is the expected internal. Therefore, it says that the expected, because this is true for any advisory function, we can say the expected internal regret at time t in the at most summation of R. There is a high probability proof of this statement as well, and I'm going to tell you next what is this. There is a high probability proof of this statement, which I'm not going to show you using some sort of martingale argument, but this is kind of like the expectation argument, which is simpler and has the core idea. Now, think of these RIs. So what are these RIs? So the RI is the regret bound that you can get in the online learning corresponding to algorithm I. So if you remember from last lecture, even though we had this bound, which was a square root T log n, we actually had a more refined bound, if you recall, which was a square root of m log n, where m was the reward of the best action in hindsight. We talked about the cost minimization, and then I told you that there is also reward maximization version. But I just upper bounded m with t, assuming that the rewards are bounded between 0 and 1. And by the way, so in this lecture, all the rewards are also bounded between 0 and 1. But really, like the regret bound that we have are external regrets, not as a function of t, but as a function of r. Let's say this is the total reward that you get. What we showed is this is greater or equal to the square root of r times log n. If you don't recall, go back to your notes, and then you will see we have the expression for the maximum loss. M was the number of mistakes, if you remember, from the binary prediction or the hedge algorithm. And then I upper bounded that by t to get the less refined regret bound. But really, like what you can get is this. And now it's going to be helpful here because somehow the total reward of algorithm I is going to be bounded by okay, so now, okay, why is this helpful? Because somehow you know that if you add up, fix any arm, right? So if you add up the reward that you get for that arm, for all these algorithms, then they're going to be at most somehow, because you're dividing the rewards between these algorithms, if you, at the end of the day, add up all these rewards for any specific arm, then this is going to be at most t. So basically what I'm trying to say, plain, summation of Ri is at most t. It's one thing that's not summation of Ri, summation of, oh, sorry, this is the bad number. So R was regrets. Let's call that M. The summation of Mi is at most t. And your regret bound Therefore, summation of Ri, which is equal to the summation of the square root of mi log n. I claim this is going to be at most the square root of Tn log n. Why is it true? Because the square root is a concave function, right? So now, I think this is the correct inequality. If I look at the summation of the square root of xi divided by n, then this is less than square root of summation of xi divided by n. The answer inequality. And if you apply this inequality here, where you set xi to be mi log n, you get the right answer. All right. So we are going to be back in 5 minutes. Then I'm going to show you how we can actually get this whole stuff using a different tool, which is Blackwell Approachability. So let's continue. There is a lot of them each. I'm not sure how far I'll do it. Because I think the coolest part I wanted to do is the last thing.
So you showed that if you have no internal regrets learning, you're converting to equilibrium. But can be guaranteed that you are converging to this good equilibrium, not the one that is green on one side, red on the other.
No, but there's this notion of a smoothness in games, and also there's problem of choice of anarchy and choice of stability in games. Usually those results they carry over all the way to learning agents, not just. But the short answer to your question is that I'm not saying anything about the quality of the equilibrium. If there's a unique correlated equilibrium, then we are going to identify that. But if there are multiple, then they might actually end up with a bad correlated equilibrium. Having said that, there are certain games in which you have an approximate until the quality of the correlated equilibrium because of the structure in the game. For example, potential gains or condition gains or options, actually, third-party options. But it's an entire course, so I'm not going to talk about it. All right. So if you have not been able to follow me, it is the right time to restart and tune back because whatever I'm going to tell you is totally different, but then eventually you see the connection. All right, vector value games. Let me define a two-player game, both the one-shot version and so we have the one-shot version and the sequential version. Here are the game semantics. So I have player one is selecting, let's say, an action xt or x, if it is sequential xt from curly x, and imagine this curly x is a compact set. It doesn't need to be convex, but let's say it is compact. Player two pick y, which is in curly y, and again a compact set. Now the game is endowed with what I call a vector payoff. Let's call that U. So U is a mapping from pair of action, basically pairing X and pairing Y is a space, to d-dimensional space. Should let's go with n-dimensional space. N will be related to the gain application. And also, I assume that U is a bi-affine function. What does bi-affine mean? So basically, if I fix X as a function of Y, it is an affine function, it is a linear function plus a constant, and vice versa. And then finally, I have what I call a target set. Target set S, where S is a subset of Rd, and I'm going to assume that the Rn, and I'm going to assume that it is compact. And actually, it's not compact. It's only closed and convex. It doesn't need to be bound. So it is closed and convex. And both of them are quite neat. So here's the game that we're playing. Here is this, say, so there is this set F, which is convex. We have the vector payoff. You're going to put a strategy X, I'm going to put a strategy Y. That is going to spit out some U. Let's say a vector like here. So at player one, if U turns out to be in S, then player one is happy, and player two is unhappy. And if it turns out that U is not in S, then player two would be happy and player one would be happy. So in terms of player one would like to play a strategy such that when player two responds, you land in the target set S, and the other one would like the final vector payoff to be outside the target set. So very abstract. Right, so now you can think of the one-shot version. So that's the one-shot version. The sequential version is kind of like that in the sense that, hey, two players are playing this game at every time t, player one is playing xt, player two is playing yt. Now, u of xt and yt will be realized. So both players, they know u, but they don't know the strategy of the player. So u of xt yt is revealed, or you can say alternatively, that xt and yt are revealed. They're not fully equivalent, but actually it turns out that for designing an algorithm here, all I need is the vector payoff to the revealed. So two players are playing, and pick xt, other player picking yt. We pick these strategies simultaneously. We get a vector payoff, and then we get to see what is the corresponding vector payoff, and then the game continues. So we sequentially play these strategies. Now, player one kind of wants to have a sequence of strategies x1 to x capital T, such that the average vector payoff is as close as possible to target set S. So now I'm going to define this notion called Blackwell approachability. So we say target set S is approachable if there exists an online algorithm in the sequential game for player one outputting, let's say, the sequence x1, x2, xt in response to sequence y1 to y capital T, such that we have the following. If I look at the L2 distance of L2 distance of average vector space and S, I'm going to define this in a second, if it at most some R of T and limit of R of T, let's say R bar of T, limit of R bar of T as T goes to infinity should be equal to 0. And what is U bar? So U bar is defined to be basically 1 over T, summation T from 1 to capital T, U of xt and yt. So this is a vector in R to the n. Right? There's a lot of notation on the whiteboard, but it's actually quite easy. All I'm saying is that we say a target set S is approachable if there is an online algorithm, like player one, that has a strategy generating x1 to x capital T against, let's say, given adversary is generating y1 to y capital T, such that regardless of what adversary is playing against player one, regardless of who is player two, you always guarantee that, hey, the average distance of the vector payoff at X is at most this quantity that converges to 0. So as long as this average distance goes to 0, you call this game, we call this target set approach. Is the definition clear? Now, let me define something else, which is a much stronger notion. So we say a target set S, and every time I say target set S, in your head, assume it is a closed convex set, as I define in the definition. The target set S is quote unquote forcible if there exists a super powerful strategy for player one, if there exists an X such that no matter what player two does, the U of X and Y will be S for every Y. So we say target set as forcible if there's a super powerful strategy for player one that forces the other player, not forces the vector payoff to be always in S, regardless of what player two. Make sense? Right. So let me define something else. So half a space approachability. The geometric picture I would like to have is the following. So imagine you have this set S. Many times I consider different half spaces that they contain. For example, what is a half space? It's being defined by a hyperplane. And I'm looking at this side. So I call this a half space H with this normal vector that actually it's this normal vector that contains S. Right? So that's a half space containing the convex and closed sets. Another picture that we are going to use a lot is, let's say, for example, target set is negative vortex. But this is S. The negative orthant is going to be closed, but not going to be bounded. It's not complex. And then the half spaces we consider, they probably look like this, right? So something like this. This is going to be a half space H that contains this. Yes.
When you say in response to sequence one, you assume that the player one knows the action of player.
No, so they're playing this game sequentially. So as I mentioned here,
So one is
so
playing.
at time t, only thing that you know as player one and player two is the history of play.
And then that should be true for any.
Any adaptive
Any
adversary that is generating by multiplication. Any adaptive adversary generating by multiplication. This is why I wrote it down kind of like that. Yeah. I'm not 100% mathematically rigorous yet. I assume that you guys already know what they mean by in response to sequence, which basically means you have two players, they're playing a sequential game, similar to exactly, the mathematical rigor that I need to show everything is at the level of the zero-sum game that I analyzed last time. Everything is kind of exactly like that. You assume the adversary is adaptive based on the history and the realizations of the strategies of the algorithm can make a decision, so on and so on. But in some of the proofs, I'm going to wave my hand a little bit and assume these strategies are deterministic so that I won't need to work with the martingales. Everything will be the same when you want to show the results and expectation. For high probability results, you need to be careful about underlying martingales. So I'm not going to be that careful. You will have an assignment that will take up. So half space approachability. So we say target S is half space approachable. If and only if the following is true, for every half space H containing S, H is approachable. So one direction is trivial. Basically, if S is so pick up half space approachability versus approachability. If something is approachable, then this is also going to be half space approachable, right? Why? Because, well, so I can approach a subset, therefore I can approach a superset. Is it clear? So if you could devise a strategy that you get close to S is already in your half space, you could get very close to the half space. So in some sense, half space approachability is more relaxed than approachability. It turns out that it's not. That in fact, one is equivalent to the other. So theorem, which is basically what we're going to show. Blackwell approachability theorem. It says approachability is equivalent to half space approachability. And if S is approachable, and assume that my reward for any x and y is basically in L2 ball with radius 1. And also S is a subset of L2 ball with radius 1. Then we can approach at the rate of 1 over 1 over t. Basically, R, did I use RT? R bar T. So R bar T, there exists an algorithm. There exists an algorithm that you can run actually fast as long as you have access to the temperature microwave for now, portable computation. There is an algorithm such that R bar T for that algorithm is at most I believe something like 2 over square root of T. You can do even better. But the version that Blackwell showed, and I'm going to try to give you the 2 over square root of T. Right. And so far, it might not be super interesting. Let me show a demo, and then I'm going to show you the application of the Blackwell Approachability first, and then I'm going to show you how it's actually going to operate. The lemma, which turns out to be quite helpful with the process. The lemma half a space H is approachable. Then let me drop it in. Half space H is approachable if and only if the following is true. H is forcible. Let me focus on this one. So if half space H is approachable, we can actually show it is forcible, which means there is a universally good strategy for that half space. And vice versa. And the other, this is actually trivial, right? So if H is forcible, of course it is approachable. If you play with that forcible strategy, you're going to approach immediately. But the interesting part is the other direction. If you can show the approachability of a set H, if you have a space H, then it should be forcible. Now, here is how an engineer would look like Blackwell approachability theorem and this lemma. So we're saying, okay, so we want to check approachability. So it is equivalent to half a space approachability. And then half space approachability is equivalent to basically something like this, right? So if H is approachable, then it should be forcible. Then here's how you can think of the entire approachability. If I give you a target set S, and you would like to see whether it is approachable, then all you need to do is the following. Check all the half spaces that contain H and show they are forcible. So if you check all the half spaces that contain S, and then you show that they are forcible, which means for each of them there is a good strategy for player 1, then you're done. There is an algorithm for Blackwell approachability based on the theorem that you can run to approach the set, and everything is good. It turns out actually this algorithm is using the lemma in a kind of cute way. But before showing you how this is true and why this is true, let me show you some of the applications. In particular, how you can actually get external and internal regrets by just simply looking at Blackwell approachability. And if time allows, I'm going to show you the algorithm. If we won't have time, then I'm going to maybe upload a note about an algorithm called regret matching, which is the one that gives you 2 over square root T. It's a super easy algorithm. Okay, so let's go with the applications because we talked about correlated equilibrium and internal external regrets. Application 1. No external regrets on the learning. I'm going to define a game that once you show it, this game is approachable, then basically you have an algorithm for for online learning when you just consider no external. Right, so it's going to be a Blackwell game similar to the one that we discussed so far. Player one basically selects an arm or action. Therefore, if I think of the pure strategy space, we call that X hat. This is basically the numbers 1 to n. And then the actual S, the space of all the mixed strategies, mixed or randomized strategies, would be n-dimensional fields. All the vectors of size n that is not to ones, none. What the player 2 does, player 2 picks the reward function. Picks the reward function in the online learning problem. So remember, player 2, for some time t, is assigning a reward to each arm. So it's gonna basically pick, let's say y is going to be equal to 0, 1 to the n. So this player is going to pick a strategy P, which is part of delta n, and this player is going to pick a strategy R, which is 0, 1 to the n. So this is the distribution or n discrete objects. This is rewarded. Think of it in this way. So what is my target set S? S is nothing but the negative orthant or negative n-dimensional negative orthant. And then I'm going to define my utility in the following. So utility for, let's say, a pure strategy I and a strategy R. I'm going to use hats because this is not the final utility I'm going to use for the Blackwell game. The U hat of I and R is defined in the following way. So it's going to be equal to basically the reward I get if I play I versus the reward that you get by playing each R. So this is going to be RJ minus RJ minus R1 minus RI, R2 minus RI, all the way to Rn minus Ri. I can write it down. So let me write it this way. So I'm playing I, and adversary is playing R, which tells me the entire vector. And then in each row, I'm looking at basically the loss I have if I had played that row. So if I play 1, R1 minus Ri is basically the regretted. If I play 2, R2 minus Ri is the regretted. So now the real U that I'm going to use for P and R is essentially the expectation of this vector. And by the way, so these are all vectors, right? So everything is vector line. So you're going to be expectation of U hat I and R when I is drawn from P. So this is going to be basically the following. It's going to be, again, R1 minus R dot P, R2 minus R dot P, Rn minus R dot P. Like it's basically the vector R minus R dot P times an all one vector. Is the game clear? A few things to check. This is compact. This is compact. S is closed and convex. It is closed. U is biaffine. It is biaffine. Right, so if I fix P, it's going to be linear as a function of R. If I fix R, it's linear as a function of, is affine as a function of P. So if I fix P, it's going to, yeah, therefore it is biaffine. Now, let's see why it is approachable. So in order to show its approachability, all I need to show is that for any apostate containing S, that apostate is forcible, or let's say approachable. Let me go with a picture. So this is the picture I want you to have in mind. So this is S, basically the negative vortex. Now, we know this is approachable if any half space containing this guy like this. For example, this side is approachable, right? Somehow, I'm going to actually look at all the half spaces that have origin, simply because if I want to show, let's say, the approachability of this half space, if I can show the approachability of this half space as in. So without the functionality, I can just restrict my attention to half spaces that pass the origin. Right? Let's think about one of these guys. Let's say the normal vector is something like this. Depends on how you look at this direction or that direction. So this half space is basically defined. So A transpose A dot product Z is less than or equal than zeros. Right? So that's this half space. Now I'm going to show that for any choice of A, so this is what I'm going to show. For any A, there exists a choice of P such that A dot product U hat of P and R is less or equal than 0 for any R. That's the forcability, right? So no matter which half space you're looking at, there always exists a strategy for this player such that the U hat lands in that half. That's what I'm going to show. This is not what I'm going to show. I'm actually going to show something much stronger. I'm going to show there exists a pi P such that A dot U hat is actually equal to 0. Let's write it down. So A dot U hat is equal to A dot product with R minus R dot P all 1. I'm just going to write it down because I don't know, that's how I think about it. So summation over I minus summation over I and J AI times summation, let's say summation over I and J AI times RJPJ. Let's see if we all agree with that. Because so this is like summation RJPJ, summation RJPJ, summation RJPJ, and then you look at the dot product and that's going to be basically summation over I and J, AI, RJPJ, or all I and J. And the first one is summation over. So this is equal to the summation of RI times AI minus summation times pi times summation over j aj. Let's say we all like this. Here, I just replaced the role of I and j, so wrote it down as summation I and j, aj, or pi, just rename my variable. So now we have summation ri pi and then sum over j rj. Right? So now the strategy is clear. So if I set pi to be equal to ai divided by summation aj over all j's, or in other words, if I set vector p to be basically vector a, which would be in positive order but normalized so that summation equal to 1, then this is going to be what we have. So the set is approachable. This set is approachable. Now let's see by itself online learning. So let's say this is approachable. Therefore, we know there is an online algorithm in generating a sequence of the strategy x1 to xt. Such that against the adversary that goes with the am I using X or sorry, let's go with A. So generating a sequence of action. Oh, I'm so sorry. Let's change this to alpha. I'm using A for actions. It's an honest mistake. So let's call this guy alpha. Alpha I. Alpha I. Alpha, alpha, this is alpha, alpha. This is an artifact of not having nodes. So approachability, there is an algorithm, there exists an algorithm generating the sequence, let's say A1 to A capital T of actions, such that for any adversary generating the sequence of rebar vectors R1 to Rt, I think of these actions as each of them is a randomized strategy over an actual pure action. So there is an algorithm generating A1 to A capital T such that for any adversary generating R1 to R capital T, I know the distance of U and S is at most R of T. Now let's understand U. So what is U? So U is basically the following. U or U bar is going to be the 1 over T summation T from 1 to capital T U hat of T, which is going to be the following. So it's going to be R summation RT1 over all T's minus summation over T RT dot product AT, and then you have summation RT I over all T minus summation over T RT dot product AT. We think this is anything that we get with respect to action 1, we get with respect to action 2, we get with respect to action N. So now, if the L2 distance is at most RT bar, look at S. So S is a non-negative orthant. So if I know the distance of a vector, the non-negative orthant is at most something, then I know every coordinate, let's think of the some of them are negative, some of them are going to be positive. If something is negative, then that's fine, so it is at most 0. If it is positive, then it cannot be more positive than R bar T. So therefore, from this, I can conclude that for every I, in fact, summation of RT I minus summation over T RT dot AT, so there's one over T here, so divided by T is no more than RT bar. And that's on there. You rearrange the term, that means the expected revenue, expected reward that you get is at least the reward of best action minus T times R bar, that's the total. So that was easy. Let's go with the application number 2, which is no internal regret. Before getting there, let me comment on how to get an actual bound for no regret online learning. Assume that we have Blackwell theorem, so assume Blackwell's rate of, let's say, order 1 over square root of T after normalization, right? What does normalization mean? Normalization. So you need U to be in L2 ball of radius 1, and you need S to be a subset of L2 ball of radius 1. So I could modify the game a little bit so that rather than negative or 10, I'm just having these guys, because you never would have been able to reach anything beyond that point. So that's not gonna make a difference. But for you, right? So in the online learning, we assume each of these rewards is between 0 and 1. That doesn't guarantee that you're in L2 ball of radius 1. But if you normalize the reward by a square root of n, then you get that. So note, start by normalizing, which means I'm going to start with normalizing RT by dividing by a square root of n. So I'm going to divide all the rewards by a square root of n, so that I have an instance of the Blackwell approachability where the U hat is in ball of radius. Actually, I need to divide by, so this is the number between 0 and 1, this is the number between 0 and 1. So this whole thing is the number between -1 and 1. So L2 norm of this guy can be as large as 4 times n. So I need to divide by 2 square root of n for the time thing. So if you do that, then you ensure your utility is going to be between 0 and 1. All right, so now what RT is going to be? RT of the Blackwell approachability, as I said, is going to be something like order 1 over a square root of capital T. But this is only after you normalize by dividing by a square root of n. Therefore, final regret that you get with this approach is going to be a square root of T times n. So you get order a square root of T times n. There is some constants. Okay. Let me repeat myself. After you normalize, your regret average regret bound is going to be order 1 over a square root. That means your total regret is going to be order a square root. But you already normalized by dividing the reward by some constant times the square root of n. That appears linearly in the regret bound. Therefore, your final regret is going to be a square root of T times the square root of n times some constant, which is what you have. And this is not the best thing you could get for external regret, right? So we already know multiplicative rate update gives you a square root T log n. And there is a paper that shows how with Blackwell approachability, different algorithm for Blackwell approachability, you can actually get a square root T log n. I'm not going to show you that. But this version is enough actually for getting the optimal extent, the optimal internal. And this is what I'm going to show. So no internal regret. pretty much, maybe share thoughts. There is going to be a lot of similarities, but no, there's some difference as well. Can I erase this part as well? Okay, floating plans. All right, so what is this new game? So no internal regrets. So we have two players. Very similar to the previous game. Let me write it quickly. So X is going to be again n-dimensional simplex. We also define the X hat, which is the number between 1 to n, as a space of pure strategy, but we really work with X. Again, Y would be 0, 1 to the n, exactly as before. So this is player 2 is going to pick R. Player 1 is going to pick P. So this is player 1. This is player 2. I'm still gonna use kind of the same target set, but before that, let me tell you what is the utility function. So my vector valued game this time, rather than being in n dimensions, but in n squared dimension. So I'm going to define, let's say, U hat of a strategy K played by this guy and R played by this guy to be a matrix in Rn by n. So matrices are vectors, right? So I'm treating this as a vector value game. So my payoff pairs maps a pair of strategies into this, but really all I'm going to use is the U, which is for the mixed strategy to maps P and R to R n by n, and I'm going to basically say that the U of P and R is expectation of U hat of K and R when K is drawn from P. So I'm going to tell you what U hat is. And then U is defined using this expectation. So what is U hat? So U hat of K and R. So remember, so for external regress, somehow a U hat of K and R was how much I'm gonna lose if I switch to a fixed strategy I. U hat of K and R coordinate I. How much you're going to lose? How much you're going to gain maybe if you switch to a fixed strategy I. But now because we are thinking about internal regret, it is about, hey, how much I'm gonna lose in rounds I'm playing J if I switch to I. That's swap regret or internal regret. So I'm gonna now define the function. UKR at coordinate I and J. Think of these as deviating a strategy. And think of these as your current strategy. So this is going to be equal to R of I minus R of J, but only if K is equal to J. I'm looking at the micro foundations of internal regret, swap regret, and by just interpreting what that solution concept means, I can actually write down this vector payoff. So it's going to be the deviation I get from J to I if I'm playing J. Deviation utility I get by playing I instead of J when I'm playing J. And now we can write down these numbers in a matrix of size n by n for any pair of strategies. And I can define U of P and R to be basically equal to, if you take expectation here, so it's going to be, if I'm not mistaken, R of I minus R of J times the probability that K is equal to J, which is equal to Pj. Is it clear? So R of I minus R of J. Let's do things in the reverse order. So let's first see why if we are approachable, then this is going to give us no internal regret or no swap. Kind of the same argument as before. Let's say distance of U bar and S, the negative or I didn't tell you what S is. So S is going to be negative portent for matrices of size n by n. So you ideally like all these numbers to be negative. Now, if the distance of U bar and S is smaller than some R bar of T, then you can say for any pair of coordinates I and J, think of the definition of the correlated equilibrium, right? So for any, or the definition of swap regret, for any pair of I and J, I know U bar of I and J is smaller than R bar T. And therefore, we can say 1 over T summation T from 1 to capital T RTJ minus RTI minus RTJ times the probability that at this round, my action AT was equal to, so there's a random, the probability that IT is equal to J, where IT is drawn from 8. That's basically this is going to be U bar, and you say this is the smallest R bar T. And this is just, therefore, R swap regret is going to be at most T times R bar T. And then we are done. And in terms of normalization, in fact, we need to do essentially the same normalization as before. So that you are in n times n dimensional ball of radius 1. And that appears as a square root n here, so you end up with getting a square root. So with normalization, it's essentially same normalization.
I think that at the end you said that is
No. Yeah, so it's going to be this, if you write it down, you'll see. Because I want to cover everything, so let me actually not do the normalization. It's just same normalization divided by 1 over the square root of n. And use the fact that is the definition here. So so the difference is that now you have Ri times Pj. So they sum to 1. So same normalization problem. It needs a little bit of algebra, but trust me, if you normalize by dividing by 1 over square root of n, then you see that norm 2 of this matrix, summation of all the entries squared, would be basically bounded by some constant. Therefore, It says that this is before normalization. So after normalization, it says R of block P becomes a square root of n times T times R bar of T. And if we use that Blackwell approachability theorem, this is essentially going to give us a square root of T times n up to some constant. Now I'm going to show you why this is approachable. And this is quite cute. I have some connections to existence of explanation distribution for transition kernel, but it's not exactly that. Because if you remember from Blum and Mansour's paper, as part of the algorithm, you needed to show that any transition kernel has a stationary distribution. And showing that any transition kernel has a stationary distribution needs a proof. As we are showing the approachability, you will see something similar to that with appear here, but it's not exactly that, but the same proof for showing the existence of a stationary distribution of transition kernel is what I'm going to show here, what I'm going to use here in order to show the existence of a forcability strategy for half spaces that contain negative orbits. And then, if we have time, I'm going to quickly show you what the algorithm is, maybe even the analysis. So why S is approaching? The same geometric picture in your head, assume this is n by n dimensional space. I don't know how to draw anything that can give you a better visual perspective. Okay, so this is going to be S. And I'm again looking at half a space that has the origin. Let's say a normal vector A. This time A is going to be R plus n by n. That's really what's happening. So similar to before, I'm going to show you that there exists a strategy P in delta n such that A times U hat is again equal to 0. For in matrix form, I'm going to show you that summation over all I and j, Aij times U hat of ij. Be very careful. So this like U hats at the points P and R, but I'm looking at the entry ij. And so U hat maps a pair of strategies to a matrix. I'm looking at the ij entry of that matrix. That's the notation this. So I want to show this is equal to 0 for any choice of R. So basically, yeah. Correct. So fix A, there exists a P such that this will become 0 regardless of what R is. Let's do the thing as before. Right, so here. So what I'm going to show you the fact. So I'm going to show that the summation over I and j, Aij times Ri minus Rj times Pj is equal to 0. I will find a P such that it is always equal to 0 regardless of choice of. All right, so what does it say? So it says basically that Yeah, so summation over all I of Ri times summation over all j of Aij minus Pi Did I make a mistake? Oh, I can see, sorry. J. Good, so this times Bj. Or I comes out, and then you have summation over J of Aij times Pj, exactly. And then you have minus Pi times summation over Aij over all j. Is that correct? No, it's Aj. That's the part that it's not the transition. If it's both Aij, all I need to show is existence of special distribution transition. Let's see if you're agreeing with my calculation. So, summation here I didn't do anything. It's just summation over I, Ri, and then summation over j, Aij, Pj. That's the first term. For the other term, I renamed I and j. So swapped the name of I and j. So I have Ri times Pi summation over j, Aj. Okay, so now this is kind of interesting because we can think of this as some matrix M multiplied by P, where what is M? So where N is equal to so if this is going to be equal to 0, that means for every I, Pi should be equal to summation of Aij Pj over all j divided by summation over all j Aj. So as long as we show the system has a solution, you're good to go, right? Because that makes it 0, and therefore, sorry, as long as you can show it has a solution in n-dimensional sequence, you're good. That's what we really want to show. I think my note says, let's think about some calculation last night. 18 transpose P. All right, so let me write it down and then we'll see why this is the case. Let's define a matrix M. Maybe I should define a piece of the first one. Define matrix M, which is equal to A transpose minus diagonal of A times all one. So what is A? So it's A is the matrix of all the AIJs. Or maybe AJIs. AJIs, right? So I think A transpose is what I have here as AIJ. Maybe I can use this. What? Okay, good. I think that's good. So if define M to be my matrix M to be equal to A minus a diagonal matrix around the diagonals. I'm gonna write down A transpose times 1. So A is all these AIJs that you have here. This is n by n matrix. I'm defining M like that. Then basically, we want to show that there exists a P in delta n such that M times P is equal to 0. Yes.
Wouldn't that be equivalent to, let's say we have a continuous time Markov chain and P is gonna be the station distribution of the continuous time Markov
No.
chain and AIG are the rates,
No, because this is AJI. If it was the summation over AIJ, then that would have been a transition characteristic station distribution. But this is AJI. Important. So I'm summing over J's. Suppose it was AIJ, I was summing over. You see, like this is AIJ, this is AJI. That's not by any means a transition characteristic.
I think it says the rate exiting from one state is equal to the rate entering to that state. It's just saying that.
Maybe there is an interpretation like that, but I don't see anything here. But this is basically what I'm gonna show. And maybe there are easier ways of showing this. The only way I should come up with the following. So imagine I'm defining some matrix M, which is equal to identity plus some epsilon times M. This part is pretty algebraic. Maybe there is an easier way of showing it, but let's say N is equal to I plus epsilon times. This is N by N. Now, if you look at this matrix, it has a nice property of 1 transpose times N. We can show it is equal to 0. So we know. Like just a structure of the matrix is such that you get 1 transpose times N. It's going to become 1 transpose times A minus 1 transpose times A, and it becomes actually not hard to show. And then when you look at this matrix L, another observation is the following. So every entry of M is going to be, every off diagonal entries of M, of course, is going to be positive, right? So Mij's are greater or equal to 0 if I is not equal to J. Because if I is not equal to J, the diagonals are 0, so it is just Aij. Greater column. So now L is going to be a matrix that, let's say, for a small enough epsilon, all the entries are going to be positive. Now I'm defining a map. So think of the following. So map is this, so given a vector Q in delta N, I'm going to map it to L times Q divided by 1 transpose times L times Q. Basically, I get a distribution in dimensional space, and I map it to another distribution using this matrix that all the entries are not. So this defines the map from delta N to delta N, which is continuous. These spaces are compact. Therefore, this map has always a fixed one. So there exists a Q star such that L times Q star divided by 1 transpose times L Q star is actually equal to Q star. This is pretty similar to a station distribution. Now let's see what happens. So if you look at 1 transpose times L times Q star, this quantity is equal to basically 1 transpose times I plus epsilon times 1 transpose times M. So 1 transpose times M is 0. So this becomes all 1 vector transpose. And this will be multiplied by Q star. So the denominator is going to be equal to all 1 transpose times Q star. But remember, Q star is a point in n-dimensional simplex, so this is equal to 1. Okay. Now, because this is equal to 1, we can conclude that L times Q star, which is going to be I times Q star, plus epsilon M times Q star will be equal to Q star. Therefore, epsilon times M Q star is 0, or in other words, M times Q star is equal to 0. And remember that Q star was a point with fixed points, so it was in the n-dimensional simplex at the first place. So I found Q such that M times Q was equal to 0 and Q was in n-dimensional simplex. That's exactly what we want, right? Because remember, so this whole thing is N times P when you look at rho I. So what we really wanted to was finding a P such that M times P is equal to 0. And this P is the Q star I found at the fixed point of the map this time. So it's a very quick. So let me tell you again the argument. So we set up this linear system. I wrote it down in matrix form. Now you have MP times 0. So you want to find a P in n-dimensional simplex such that MP times MP is equal to 0. Then I defined, and M has 2 properties. Mij's are non-negative for off-diagonal entries. And 1 transpose times M is equal to 0 because of just a structure of functions, regardless of the choice of A. Then I defined L, which was 1 plus epsilon times M. This is just a trick so that you have a matrix that all the entries are non-negative. And then from this matrix, I defined a map that basically gets the distribution, multiplies the matrix by the distribution, and then normalizes it to have a distribution. And this map is a continuous map from a compact space to compact space, so it has a fixed point. That's going to be Q star. Turns out that the fixed point of this map is exactly the P that we wanted to find. Yes.
Where did you use the fact that all the entries of L is one?
So that this map is well defined. So you have this point in delta M. The LQ is going to be a vector that maybe is not doesn't have L1 nor equal to 1, but still all the entries are non-negative. So therefore, if you divide by L1 norm, you end up with something in n dimensions. If some of the entries of L were negative, this would have none. So too much algebra, but I think the picture is clear. So we show that approach. This is why I said Blau Mansour is actually a genius paper, because they didn't use this machinery. And this is more of a mechanical way of approaching these kind of problems. The reason I thought that is because I really want to encourage you, next time that you face an online learning problem, think hard whether you can cast it as an instance of Blackwell approachability. Because if you can, then all you need to show is checking whether all the half spaces that contain S are forcible. And it's actually pretty mechanical at that point. Maybe the algebra becomes messy, but if there exists an online learning algorithm, you should be able to show it is approachable. And I think the power of Blackwell approachability is the if and only if part. So if for your problem there exists an online learning algorithm, this algebra should go through. You should be able to find such a P that is a forcible strategy for any given half space containing your target. as long as you set up a Blackwell game that is essentially equivalent to your original problem. This part should not be lost, it should be lossless. And this is why I said in the definition of the payoff, I was looking at the very micro foundations of the internal regret, or let's say swap regret, or let's say correlated equilibrium to kind of design this vector payoff function. Cool. So I have maybe 8 minutes. That is enough to definitely tell you what the algorithm is for Blackwell approachability problem. And the analysis is pretty much similar to how you analyze online gradient descent. I might just write it down on a piece of paper and post it on Canvas. That's going to be. I don't think there is any really innovative idea in how to show the regret bounds. You can even think of it as an example. The algorithm is also the most natural thing that you can think of. All right. Regret matching. Algorithm to solve Blackwell approachability. Pretty much a geometric algorithm. So imagine I have the target set S. Suppose I'm at some time t. And up to this point, we have some average vector payoff, right? So let's call u bar of t minus 1 to be basically 1 over t summation t from 1 to t minus, oh, sorry, 1 over t minus 1 summation t prime from 1 to t minus 1 of u of x t prime and y t prime. I'm using the notation in the Blackwell approach. Okay. So 2 things can happen. If u bar t minus 1 is in S, so you're somewhere here, then it seems you're good, right? So if, for example, the game had ended at that point, you had distance 0. So in that case, just play an arbitrary strategy. Unfortunately, someone has forced you to play the game until capital T number of rounds, otherwise you would have terminated, right? But because someone has forced you, just play an arbitrary strategy, XT, whatever that you want. Now, the interesting part is if u bar t minus 1 is actually not in S. So let's say you are somewhere here. So u bar t minus 1. Here's the most natural thing that you can do. First, project u bar t minus 1 onto S. So remember, S is a convex set. It was also closed. So in principle, if you're caring about the running time of this algorithm, if you can separate this convex problem, this convex set, you can solve this problem. So separation, what does that mean? I assume that you guys are familiar with separations and separation oracles. In optimization, if you're solving, let's say, linear functions over the space of over a convex set, or you're trying to find the feasibility of a point for a convex set, then if you have access to some sort of oracle called separation oracle, then you can solve the convex optimization using ellipsoid method in polynomial time. And there are other projected gradient ascent algorithms that they can also solve convex optimization problems. Now, what is a separation oracle? You have a convex set, I give you a point. You should be able to find the half space that separates the convex set from that one. So either you should tell me this is feasible, or you should be able to give me a half space that separates that point from the convex. And projection can also be done as long as you can have a separation oracle. So if you have a separation oracle, projection onto it, as simple as it sounds, is doable in polynomial time. If you don't have a separation oracle, this task might be even computation demand. Computation. So if F is a nice complex set, which means you have access to a polynomial time separation oracle, you can project this guy onto X. Let's say do the projection, and that gives me this point. I'm going to call it phi t minus 1, the projection. Now, consider a half space that is tangent to the convex set and passes this point and contains this. So basically, this guy. I'm going to call this half space ht minus 1. So if you want to know what is this half space, it is basically the normal vector is something like u bar minus 5. I think it is phi t minus 1 minus u bar t minus 1 dot product z should be greater or equal than phi t minus 1 minus u bar t minus 1 dot product phi t. This is defining the half space. I'm going to call it ht minus 1. So there was a lemma that I didn't also show that's going to be part of the analysis. Maybe I should prove that lemma first. So the lemma says approachability is equivalent. So half space approachability is equivalent to forcability of the half space. So if the half space is approachable, then it's going to be forcible. So imagine I'm showing a variant of the Blackwell approachability when you want to show that if every half space containing S is forcible, then you have an algorithm. Okay. So if I'm going with that direction, now I have identified this half space. So ht minus 1 is forcible. For example, in all of the results applications, we showed that that half space is forcible. Therefore, there is a corresponding strategy. Let's call that x of ht minus 1, which is the forcible strategy at that point. Now I'm going to set xt to be that forcible strategy. So it's going to be somewhere. And then what happens is that you know the next utility, by definition, not the average, the next utility is always going to land in this blue region. Because this strategy is forcible, that means regardless of what yt you realize in that round, the corresponding u is going to be somewhere here, and then it continues. So let me stop at this point. There are two things that is left to prove. One is the lemma. I leave the lemma as an exercise hint. You need to use the result of the last lecture about zero-sum games in order to show the equivalence of half a space approachability and every half a space containing, sorry, in order to show the equivalence of approachability of half a spaces and the fact that the half space is forcible. It is basically a statement about a one-dimensional zero-sum game, which is a special case of Blackwell games, quite easy. And then the second one is showing the real bound of this app, showing it is 2 over square root t. I'm gonna post something on Canvas for this part of the analysis, and I leave the other one as an exercise. Maybe I also add that, but think of it as an exercise. It's gonna be easy to prove that then. This is also not difficult, but maybe you haven't seen how people analyze the regular bound of first order methods. If you have seen those, it should be a straightforward one. And with that, I conclude the lecture. Thank you so much for your attention.